for methyl benzene. Methyl benzene. So this is the structure of toluene. Alright, so we are going to be looking at the synthesis of benzocaine being the first selected drug for this particular tutorial. So I already told you that benzocaine synthesis occurs in 4 steps. So we have number 1, it starts from the toluene. We use toluene to begin it, and then what we have in that step is an electrophilic substitution. So prior to this time, you should already know about electrophilic reactions and nucleophilic reactions in the aromatic ring. So you should be able to know that, and then you know that toluene is a common name for one of the structures of benzene, which are still going to be seen as we make progress in this particular tutorial. The next thing that will cause is the oxidation of the methyl group on the toluene. This is a methyl group, CH3. And then the next thing we have is a Fischer esterification reaction. So an ester is being formed. Remember, benzocaine is an ethyl ester of para-aminobenzoic acid, as PABA. So the next thing is now reduction of the nitro group to an amine group, and in that way we have our benzocaine, which is ethyl 4-aminobenzoate or ethyl p para-aminobenzoate. So let us look at it. So this first step is for step 1, number 1. This second equation of reaction is for step 2. This is for step 3, and then this is for step 4. So we're going to be going through how all of these reaction processes occurs that leads to the formation of benzocaine. So as I said, this first step starts from toluene. So this is toluene. Toluene is the common name for methyl benzene. Methyl benzene. So this is the structure of toluene. So toluene is the start material. Some other tutorials you can look at can actually start from para-aminobenzoic acid. So, but from the very scratch, you most likely use toluene. Another substance that can be used as a starting material is paraxylene. Paraxylene can be used as a starting material for this. So, but in this particular tutorial, we are using toluene. So, depending on when you are watching this particular video, the one that is recommended by your lecturer is what you should work by, but the principles are almost like similar. So, and if we're starting with toluene, then this is what you have there. So, for toluene, the first thing we do is to use a mixture of nitric acid. So HNO3 is nitric acid. Is nitric acid, that's the common name, that's triazonitrate 5 acid, and then H2SO4, like common name, is sulfuric acid, which is the tetraozosulfate 6 acid according to the IUPAC. So nitric acid and tetraozosulfate 6 acid is added to toluene, and the idea of adding it is for us to have an electrophilic substitution. So this is what happens here. The nitric acid is protonated. The nitric acid is protonated to form this ion. The nitric acid is protonated to form this is a nitronium ion. So the nitric acid is protonated to form a nitronium ion, and this nitronium ion is the electrophile. We have for this electrophilic substitution. So the protonation of the nitric acid produces the nitronium ion that is the electrophile for the electrophilic substitution. Just a very casual way to want to describe an electrophile. We talk about an electrophile as something that actually accepts electrons. So an electrophile accepts electrons. So it works by the addition of electrons. So this thing is electron hungry. Yes, and that's what facilitates the reaction process. So because it's electron hungry, it looks to find where it can say a donor electron and then fixes itself there. Then another thing again is that it wants to now attach itself to this, because there's going to be like an attack on the toluene by this electrophile. It's a substitution reaction, so it simply means that one hydrogen has to be out so that we can have the structure in place. All right, so then the in the toluene ring, that's the methyl benzene ring, what we have here is CH3. Prior to this time, you most likely have seen what we refer to as ring activators and deactivators. So you'd have most likely heard of ring activators and deactivators. And just in case you have not heard or seen it yet, there are videos that will explain that to you. So but I'm going to be giving you a brief overview of what we have here. So ring activators in the benzene ring refers to compounds on the benzene ring that direct substituents either to the auto position or the para position. So ring activators are substituents on benzene ring that direct substituents either to the auto, so O is auto, or the para position. So we also call ring activators, we also call them auto directing slash para directing. You can write auto slash para directing substituents on the benzene ring. So those are the ones that are referred to as ring activators. But ring deactivators are those that direct substituents to the meta position. So M is meta. So we can also call ring deactivators meta directing. Are we together now? So we can call them meta directing. So if you look at the table that tries to classify some of the substituents regularly encountered on the benzene ring, if you look at the table that classified them into activators and deactivators, which are also something as auto para directing and meta directing, you will find out that the methyl group is a ring activator. That means it will most likely direct any substituent that is trying to attack the benzene ring either to the auto position or the para position. Now, when we say auto directing or para directing, we do not mean that entirely there will be nothing like meta directing, but it means that in the event that we have a ring activator on the benzene ring, the positions that will be most likely favored for the reaction will be the auto position and the para position. You may have traces of traces of meta, but it's not as significant as that of auto and para. In same way, when you have ring deactivators, you may have traces of auto and para, but you have major part of it as meta. So because the CH3 is a ring activator, it means that the nitronium ion that is attacking the toluene ring will most likely either go to the auto position or go to the para position. But what we need for this synthesis is the para position. So when you do the production, like run this first step, you have your nitric acid, your sulfuric acid with toluene, you will have product that is para. You will also have, because this is like para toluene or para methyl benzene, or this is para nitro methyl benzene or para nitro toluene. That's what you should call that now, para nitro toluene. So you can have the para position for this, you can have the auto position for this, and probably a few meta position. Using fractional crystallization and distillation, it can all be separated in the lab. But for the purpose of this lecture, we're not doing any lab work here. So what we'll be using at the end of the day, after the fractional crystallization and the distillation, is that you're going to be using the one that is on the para position. So we have gotten a product here. The next thing we're going to be doing is the second step, which is what? Oxidation of the methyl group on the ring. So this is the methyl group we want to oxidize. What is oxidation? There are, if I'm not mistaken, about 3 or 4 definitions of oxidations we have, depending on if you are defining based on oxygen, if you are defining based on hydrogen, if you are defining based on electronegativity or electropositivity, and if you are defining on the basis of electrons. Yes, so those are the 4 different ways you can explain oxidation. So, but for this particular case, let's use the 2 definitions. We're going to use the definition of oxidation according to oxygen and also according to hydrogen. So oxidation simply means addition of oxygen, and according to hydrogen, oxidation means removal of hydrogen. So what is going to be happening here is that oxygen will be added, and hydrogen will be removed. So, and the reagent you're going to be using here is the chromium 3 oxide. Chromium 3 oxide is also referred to as chromic oxide, and it is a strong oxidizing agent. That means it causes things to get oxidized while itself is reduced. I hope that makes sense to you. So we have the chromium 3 oxide, chromic acid, that causes things to get oxidized while itself is reduced. Now, it will interest you to know that there are other reagents that can be used to achieve this. For example, the use of oxygen and acetic acid can also be explored in this particular process. So depending on what your lecturer specifically tells you or communicates to you, that is what is supposed to inform what you use in responding to his or her questions in the examination. So, but on a very basic level, chromium 3 oxide or chromic acid, chromic oxide is very, very useful in this particular step. So the chromic acid is an oxidizing agent. It donates oxygen. Yeah, it donates oxygen here. So you now realize that you have more oxygen added and then hydrogen removed to now get your carboxylic acid functional group. So you now have COOH. So you now have the carboxylic functional acid group. I hope that is making sense to you. So the thing here is that if you start this process, with the chromic acid before you do this, you are going to have this first of all change to benzoic acid, and by the time you want to now do the attacking of the nitronium ion from what you have from the nitric acid and sulfuric acid, you will no longer be able to direct it to the ortho or to the para. You will now be directing it to the meta, because the carboxylic acid functional group is a strong deactivator, is a strong meta directing substituent. So it is going to move the nitro group to the meta position, which is not what we want. What I mean by that is that if you started with the chromic acid before you now do this first step, you are going to be having a product that is this way. You know, after doing the chromic acid oxidation, what you're going to have is COOH. Then when you now do the nitric acid and sulfuric acid combo, what you're now going to have is now going to be something like this. Because it is a meta director, you're now going to have something like this. You have the COOH and then you have your NO2, which is not what we desire. So that is why it is important for us to start with the first step, then before we go over to the oxidation step. All right, so that is why we have to start with this step before we go to this step, because this group is going to be a deactivator and we don't want that. What we want is something like this. So now we're done with the oxidation step of the oxidation of the methyl group to the carboxylic acid functional group using the chromic acid or chromium 3 oxide, as the case may be. We're now going to have the Fischer esterification process. So this is where the esterification process occurs, where the ester is formed. Remember I said from the beginning that benzoic acid is the ethyl ester of para-aminobenzoic acid. So what you already have here is not amino, para-nitro-benzoic acid, because what we still have here is still like our nitro group. Well, at the end of the day, we are going to convert the nitro group to the amine group for it to now be like an aminobenzoic acid or aminobenzoate, as the case may be. So for us to get the Fischer esterification reaction done, we need two reagents. We need the ethanol. ETOH is one chemical way of writing ethanol, but the real formula or the main formula for ethanol. So let me clean this so I can have a space for it. So the main formula for ethanol is C2H5OH. So this C2H5 is abbreviated to ethyl. Is that making sense to you? So that's how we have ETOH. So whenever you see ETOH, what is simply telling you is that we are talking about ethanol. So you have ethanol reflux together with sulfuric acid. So H2SO4, that's tetraoxosulfate 6 acid. So sulfuric acid and ethanol are the two reagents that are being used here. Now the process, the intricate process that finally leads to the replacement of the hydrogen of the carboxylic acid with the ester group is not something we can be able to look into in details, because there will be need for some form of reaction to work on the ethanol, and then there's a series of transitions that occur before finally we now have the ethyl group attacking the hydrogen of the hydroxyl part of the carboxylic acid. So you can actually look that up if you want to get details of the whole movement of ion process that occurs in the process of getting this C2H5 from the ethanol moved down to this part of the compound we are dealing with. You can actually look that up. It's actually very interesting. So, but for the purpose of this video, we're not going to be looking at aspect. So basically, the C2H5, that's the ethyl group from the ethanol, is being added to the CaO, the carboxylic acid group. So when you have an alcohol reacting with an acid, what you most likely have is an ester, a carboxylic acid. What you most likely have is an ester. Remember what is the structure of the ester? We said that the ester is, we have our O, then we have our O, and then we have our R. So the R is the alkyl group, and in this situation, the alkyl group is coming from the alcohol. Let me just run you on a very quick equation that will help you understand what I'm talking about. So when we have a carboxylic group, when we have a carboxylic acid group, so we have say we have COOH, we can call this ROCOOH, whatever carboxylic acid it is, and then we have an alcohol. Yeah, so if it is C2H5 is an ethanol, if it is CH3 is a methanol, if it is C3 H whatever, it becomes propanol and the likes. So what we have here is all we have here, we can call this RS so that we can differentiate. So what we're going to have here will now be something like R C O O R S plus H2O. So this is the ester added together. So and the RS, the reason I added is just to differentiate the R from this. So the RS is coming from the ethanol or the alcohol we have in that situation. So in this case, our RS will now be the C2H5. So this C2H5 replaces the hydrogen we have on the carboxylic acid, which is this hydrogen we have here, and automatically we have this. So this is an ethyl ester. You can already see that we are about to have our benzocaine fully formed. So in this particular structure, we still have our nitro group, which is not what we desire, because this is ethyl 4 nitrobenzoate, or you can call it ethyl para nitrobenzoate. But what we need is ethyl para-aminobenzoic. So we need to reduce the nitro group to amine group. So that is the fourth step in the process, which is reduction of the nitro group to an amine group. And we can actually also use different substances to achieve this reduction. Of course, there are different reducing agents. So, but in the context of this particular tutorial, the reducing agents will be employed, working with tin that is mixed with hydrochloric acid. So we're working with tin, the symbol for tin is Xn. So tin with hydrochloric acid will be used as the reducing agent to reduce NO2 to NH3. Remember, in the definition of reduction also, you also have 4 different ways, but the 2 ways we can use to define it in this context, we can say reduction is the removal of oxygen and reduction is the addition of hydrogen. So you can already see that the oxygen is out and then you're having hydrogen. That is reduction basically. In this context, this is what we are using. So depending on what your lecturer teaches you, use what your lecturer teaches you, because he can choose to change the reagents here. The reagents is not the matter, because the reagents, there are different kind of reducing agents that can be utilized. What is important to you is, do you know what is happening? It's a reduction reaction, and what is reduced? The nitro group is reduced to what? The amino group. So now we now have our amino group, and this is our benzocaine. So what is the IUPAC name of benzocaine again? We said that benzocaine is ethyl 4 aminobenzoates. Ethyl 4 aminobenzoates. And we can also choose to call it, we can also choose that we are going to call it something else depending on what you prefer. You can choose to call it ethyl para-aminobenzoic. So why is it 4? Because you start counting 1, 2, 3, 4. If you choose to go this way, it will also be 1, 2, it will also be 2, because this is 1, so it will also be 2, 3, and then 4. So ethyl 4 or ethyl para, because it's in the para position, aminobenzoate, and this is our benzocaine. So this is basically the synthesis of benzocaine. So we're going to be going to the next one, which is sulfanilamide, so we can be able to make progress.